you need to develop the sweet skill of being able to look at chemical A and chemical B and predict, if we mix these things together, what is going to happen. Well, that's the part of the skill you're learning here in predicting chemical reactions. Of course, there are some details here you need to remember at the beginning. Things like, why do we write chemical reactions, or what are chemical reactions? Well, chemical reactions are processes in which atoms rearrange to form something very different. And the chemical reaction shows us an overview of that change. Now, we did study that if you look at something like lithium plus chlorine makes lithium chloride, and let's see, it seems like we need to have it balanced like that, that really takes a series of steps in which lithium is ionized and chlorine is broken apart and ionized, and all of these things happen. So remember, we show here an overview of a lot of chemical reactions that are multiple steps. And we can make an estimate of the energy involved in these processes by adding the energies involved in those individual steps of things like breaking bonds and forming new ones. So remember the chemical reactions that maybe you've looked at, like maybe we put a gummy bear in molten potassium chlorate. It releases a lot of energy. There's a change in temperature of the surroundings because the exothermic reaction releases energy to the surroundings. Or in the case of adding a base to phenolphthalein, it changes the color of the phenolphthalein, or changes the color of cabbage extract. Those kind of changes in color are evidences of a chemical reaction. Changes in odor. Sometimes we've been very careful with odors and we don't tend to smell a lot of the chemistry we make, but the release of many gases in chemical reactions will produce a detectable, and in some cases a detestable, odor. Yep, the production of gas, like when you put, let's say, magnesium ribbon into hydrochloric acid, and you get little bubbles of hydrogen gas coming up. Well, that's an indication that we've rearranged the atoms and made some kind of chemical reaction. Not going to take time to balance this and everything, but okay, I'll take time to balance it. Formation of a solid, as in making it precipitate. So this is what we would have looked at if you'd mixed silver nitrate and sodium chloride. We get a precipitate of silver chloride. That solid is formed. These things are in aqueous solution, and we form a solid in this process. And that's an indication that we've made something new. So when you're representing chemical reactions, you need to be sure that they represent as accurately as possible the truth. And in the case of shown here, iron and oxygen making iron 3 oxide, this is pretty much the truth. Now we might come in here and say, well, we need to balance this reaction, so I'm going to have to put a 2 here, and I'm going to have to put a 3 here, and a 4 here. Did I get that balanced right? 4 oxygen, 4 iron, 6 oxygen. We've got to use the formulas and symbols correctly. We put the reactants on the left and the products on the right. We will find, though, that a lot of reactions are reversible, and so we just traditionally say, though, the reactants are on the left. If you go to write chemicals and you write something like this, no. Gotta have the chemical formulas written correctly. So that would have to be NaCl. It has to be written correctly. The equations have to be balanced for mass. That's when we count atoms. Like here we have 4 atoms of iron and 4 atoms of iron. But we also have to balance the equation electrically and make sure the electrical charge on the reactants and products are the same. Now for AP chemistry, we often deal with net ionic equations. In fact, you have to be able to write net ionic equations. So if this is in aqueous solution, you need to keep in mind that it's really copper ions floating around in that solution and really sulfate ions floating around in that solution. So if you mix iron and copper sulfate, well, it's true that there are sulfate ions here, and there are sulfate ions here, but because they exist on both sides of the reaction, we don't need to include them. It makes our reaction a lot neater. They're not involved whatsoever in the reaction, and so we drop them out of our net ionic equation. So we use coefficients to balance the reaction, and ions and other species that are in the same form, both on the reactant side and the product side, like here we see nitrate and once again nitrate, we don't have to include those in the net ionic equation. And in fact, let's see here. I guess that's all that cancels out of this equation. So, I had a skeleton equation kind of there to start with. I checked the number of atoms and of products and reactants. Now, hopefully I can do this kind of mentally because you're going to be under the gun for time when you're writing these. And so you want to just kind of see these things mentally, write out the final answer. But you may, at the beginning here, want to follow these rules and follow these steps. Check out the number of atoms of products and reactants and insert coefficients to balance using the smallest whole number ratio. But remember, we've also got to balance the charge. And sometimes that may involve you writing things like balancing redox equation using the half reaction method, and so sometimes you may have to use that. Check to see if ions in solution on the reactants and product side and cancel if needed. And so you'll see in this equation up here we have a +1 on one side and a +2 on the other. So in order to make this reaction happen, we may need to have +2 in front of the silver so that the charges balance as well as the mass or the number of atoms. Excuse me. Remember, there are a lot of things that you have to write as diatomic molecules. In fact, there are 7 of them, and on the periodic table they're kind of in the shape of a 7, something like this, where this is hydrogen, and then we have nitrogen, oxygen, fluorine, all the other halogens, chlorine, iodine, oops, I skipped bromine. So remember, there are 7 elements that are always written as diatomic molecules. Well, hopefully that will be enough to get you started, and then we're going to look at 6 main types of reactions. Well, actually, I lied. There are more than that.